Recording, I just did that. I'll keep my mouth shut for 15 seconds. All right, it doesn't look like anybody is going to ask me any questions. So what I'm going to do is I'm going to switch to that camera up there and let's start talking. So we're going to start talking about aromatic chemistry. I did push the record button and I'll be taking pictures of the board as it happens. So let me move the chair so that I will come into it. So we're going to talk about aromatic chemistry, aromatic molecules. So this chapter is aromatic molecules. The first molecule that we talked about had this formula, C6H6, and it turned out, we went through the whole discussion, and it turned out that it looks like this. Okay. It has 3 pi bonds, and it's got a very interesting hexagonal shape. So this is what C6H6 looks like, and this is not called cyclohexa something ene, it's called benzene. It's got its own name. This guy is called benzene, B-E-N-Z-E-N-E. It's a liquid. It boils at, I believe, 78 or some boiling point around that at that temperature. It's got a single bond, double bond, single bond, double bond, single bond, double bond. So it's got, let's write this phrase because we're going to come across this sentence a few times through the lecture today. So this arrangement is called alternating double bonds, okay? So I'm just going to write it down. Alternating double bonds. That's a very important attribute or character of aromatic compounds. So keep that in your hard drive. Keep that in your RAM right now. We might need it. We might need to pull it out quite in the near future. Okay. So let me test your previous knowledge just a little bit, and I don't want you to answer me using chat. Unmute yourself and answer me just by speaking out, okay? All right, question number 1. Question number 1 has a question about the question number 1. The question is, what do you think I'm going to ask with that green arrow? Who can predict what's going on in my mind? Let's play a game. You can unmute yourself and say, Dr. Maitra, you're going to be asking about this. What am I going to ask about with the green arrow?
The degree?
On angle.
Hybridization.
There you go. Hybridization. What's the hybridization on that carbon? Speak out. Let's use a more interactive.
sp2?
sp2. Fantastic. You guys haven't forgotten. I'm proud of you. Okay, this is why I'm going to miss you guys, even though it's all online right now. I heard something really scary yesterday. What did I hear? That made me extremely uncomfortable. I heard, I don't remember which school. It's not a small university. It's a Boston University. I heard a rumor that they're planning to cancel, delete, erase fall semester. And that made me feel very uncomfortable. I'm like, oh my God, if that happens, I'm not spreading rumors. So don't put words in my mouth. This is just a rumor that I heard. Keep it to yourself. And don't put it on Facebook that Dr. Maitra said Fresno State is going to cancel fall semester. I will probably lose my job if you do that. Don't do that. I was also talking to my collaborator who works on our Alzheimer's disease project. He's in Indiana University. He said they were talking about furlough. You know what furlough means? Furlough means you don't come to work on certain days, which, well, doesn't happen in our life, but you get less paid. So you get a cut. So I don't know what the future holds. I don't think it will ever get to a point where our semester is going to be deleted. I don't think that's going to happen. I think pretty much, I think everybody's anxious. So my gut feeling is that probably the country is going to slowly open up in different parts and pockets. For example, California is probably safer than the rest of the country, except for like Los Angeles area. I heard that there are lots of new cases emerging every day. But my gut feeling is that it's going to slowly open up with strict enforcement of mask and other rules. So, like I heard that I was listening to NPR radio when I was coming to school, and they were talking about Austria slowly opening up. What they're doing is very smart. They're not opening up like big stores such as, I don't know if they exist there, but I'm just going to use them as an example, like Walmart and Target and Costco. They're not opening them up. What they're doing is they're opening up the small mom and pop shops where there are less people going to be visiting at one time. So the social distancing and not infecting each other, those rules can be more strictly enforced and followed in a smaller setup than a big setup. Like, if you open up Walmart, good luck to you, something like that. So, but our Walmarts are already open. So I don't know. I think slowly, maybe after May, maybe things will start to open up. Hopefully, there will be no new wave of outbreak. But I think we have to be careful. Probably be on our toes for the rest of the year. But then sometimes the rumors that we hear kind of freak us out. I mean, I was a little freaking out. Like, wow, that'll be really bad. SP2. Okay, what will be this question? What am I asking now? Speak up.
Bond angle?
What's the bond angle, Jason?
Oh, crap. 120, 180? 120.
What am I going to ask about the shape of the molecule, and who can predict the question and who can answer the question? You can unmute yourself and speak up. What's the shape of the molecule? They are all sp2s. What happens to sp2? Remember, whenever you have an sp2 situation, the points on the double bond, like this point, this point, this point, and the elements that are attached to those ends, like this guy and this guy, and this guy and this guy, they are, what's the word?
Planar?
Planar. They're planar. So this is planar, right? So that, and that are planar. Now again, this point, this point, this point, and this point, that's also planar, right? So wherever you look, any double bond you look, the region around that double bond is planar. So the bottom line is the entire molecule is planar, Lara. So it's like a, I don't have it here, it's kind of like a frisbee. So benzene ring is literally like a little frisbee floating around in space. That's why in aromatic compounds, when you have an aromatic compound, they sometimes like to stack. Sometimes when we look at the crystal structure that is determined by X-ray diffraction, it's really cool. You see exactly where all the atoms are and you know exactly what the molecule looks like. So when you get a crystal structure of something aromatic, sometimes we find that they like to stack. Stack means one benzene, another benzene, another benzene, another benzene. That's how they try to, kind of like make the crystal lattice. Okay. All of them are sp2. All the bond angles are roughly 120. The molecule is flat. How many pi bonds? Speak up.
3. Oh no, pi? Yeah, 3.
Three.
3.
1, 2, and 3. So 3 pi bonds. Let's figure out another math problem here. How many pi bond electrons does benzene have? 3 pi bonds. How many total number of sketchy electrons? They're not like in sigma bonds, they're in pi bonds. How many total number of electrons are present, pi electrons are present in benzene? Speak up. Number of pi electrons. How many are here? 2.
6.
There you go, 6. So total number of pi electrons in benzene, that number is 6. All right. So this is benzene. This is benzene, this is aromatic. Now the next question is, what are the specific and required properties of a molecule that makes a molecule aromatic? Okay, there are certain rules that you can think about. So this molecule has 6 carbons and 6 hydrogens. So let's look at other species that are also made out of 6 carbons. The simplest molecule, if this is energy, so that means the red arrow moving up on the left side of the screen, and it says E. That means that if I draw a molecule lower down on the board, that means it's less. It has less internal energy. It's more stable. If I draw it a little bit higher up, that means it's got little more internal energy, little less stable. So that's what it means. So if I draw, you guys can see it, I hope. If you cannot see it, you can speak up. So this molecule, let me just draw it a little bit higher up. What is the name of that compound? We have covered it in the past. Speak up, please. I see the chat is also filling up.
Hexane.
Hexane. Okay. So that's hexane, C6. What's the formula? CNH what? CNH.
14.
Yeah, C6H14. But what's the formula if there are n carbons? How many hydrogens should be there?
2n plus 2.
2n plus 2. Thank you, Richard. So C6H14. Okay. Since we are dealing with cyclic molecules, and I'm going to draw the cyclic version of hexane. Okay. The reason I drew the cyclohexane slightly above hexane, that basically implies that cyclohexane is little less stable than hexane. Hexane has more degrees of freedom, okay? Physics says that the universe is trying to increase randomness. Randomness means more chaos. More chaos means more entropy. So entropy is always trying to go up by increasing its randomness. So if I am cyclic, my randomness is less. I am more ordered. So you have always been told by your family that, do your homework, don't go nuts, sit down quietly. That means your parents are asking you to go against the universe. That your parents are asking you, if you do that to your niece or nephew or your own children, you're trying to go backwards. I'm just kidding, but then you get the point. So when you're sitting down quietly, if you're not moving around, moving your hands around, if you're just like a really nice boy or young lady, that means you're trying to decrease entropy. That's not what the universe is trying to do. So when you have more entropy, you have less energy. You have more order, less chaos. That means you have less entropy, more energy. Okay. So let's say cyclohexane is kind of here, energy-wise, at this point in the energy scale. Okay, right here. Now, what I'm going to do now is I'm going to start sticking double bonds one after another. Okay, so this is cyclohexane. Let's put one double bond in cyclohexane. And this is going to be called cyclohexene. Okay? This is important. So when you put a double bond in a cyclohexane, you make things worse because this is not what the molecule likes to do. Okay? Single bond is better than double bond. Everybody wants to be hydrogenated. Everybody wants to be saturated. So when you put a double bond, the energy goes up. It's a little more unstable than the parent cyclohexane by this much. Let's say that this much is delta E. Okay? Let's call this distance. Let's say this is delta. Delta means a small fraction. Something minus something else is delta. It's by math. So delta E means, delta E is the amount of energy between cyclohexane and cyclohexene. Okay, that's all. Now, we mess with it a little bit more. And on top of the red double bond, we stick another double bond. I'm going to turn on the fan. It's getting a little stuffy. I'm going to put a second double bond. So this is going to be called cyclohexadiene. You don't have to know. This is not part of the curriculum. I'm not going to be asking you about it. Cyclohexadiene. I'm going to put it in parentheses so that you know that this is not part of your learning objectives. Don't worry about it. But if you want to know what it's called cyclohexadiene. Oftentimes it's called 1,3-cyclohexadiene. Okay? Because you can have another cyclohexadiene. It's called 1,3-cyclohexadiene. So cyclohexadiene and cyclohexene, you put one double bond, the energy goes up by that much. You stick another double bond, energy goes up by the same amount, okay? So by sticking an extra double bond, you're making the compound more unstable by the same amount. So cyclohexane to cyclohexene, cyclohexene to cyclohexadiene, and then you would expect that this is where the fun begins. Cyclohexadiene to cyclohexatriene, you expect that it's going to go up by the same amount. It should be pretty unstable. It should be pretty unhappy about having 3 double bonds, but that's not the case. Okay, we'll talk about it in a second. So delta E, okay? No double bond, whatever energy. One double bond, it goes up by delta E. You stick a second double bond, it goes up by another delta E. Now you stick a third double bond. And you expect the energy to get screwed up by the same amount. Okay? You expect now this number is expected. expected to increase by delta E. Now you realize that, and ideally you should call it cyclohexatriene. Okay, ideally we should call it cyclohexatriene. I'm going to put it in parentheses because that's not what it's called. You know that we don't call that species cyclohexatriene, we call it, every pi bond has 2 electrons. Okay, good. You guys are chatting with each other. This is great. So it's not called cyclohexatriene, it's called benzene. And it's a special molecule, it's an aromatic molecule. So let me ask you a question. Let me see if you can jump ahead and kind of connect the dots. So the delta E from cyclohexadiene to the 3 double bond scenario, cyclohexane with 3 double bonds. So that energy we are expecting, based on our existing knowledge at this point, I'm assuming that we don't know what's going on, okay? We're kind of acting dumb. We are expecting it to be delta E. In real life, do you think that the real gap is more than delta E or less than delta E or delta E? Do you think the molecule is more unhappy, more unstable than delta E, or more stable than what we had expected? Is it better than expected? Is it worse than expected? What's going on? Anybody wants to take a shot and make a prediction, like an intelligent guess?
More stable?
More stable? So one answer is it's more stable. That means the real gap is less than delta E. Anybody else wants to agree or disagree or share your own opinion? The answer is correct. Because how do you, okay, let me see, this could be a bonus question. It doesn't carry any points at this point. So the answer is the real gap is, this is expected. In reality, the energy of, I'll try to draw it the same way. Is less than delta E, okay? In reality, the energy of this species, cyclohexatriene, or we know that it's called benzene, is less than delta E. That means this guy, I can't change colors all the time. It's also hurting my wrist. So this guy is more stable than predicted. So this weird species, cyclohexane, behaves like the way we expect it to. Cyclohexene with 1 double bond behaves like the way we expect it to. Cyclohexadiene with 2 double bonds pretty much follows our expectations, our predictions. The moment you stick the 3rd double bond and you make this cyclohexatriene kind of a species, it starts to act weird and the energy is less than expected. What other evidence have you seen that kind of corroborates, that goes hand in hand with this observation? What chemistry that you had expected this species to follow, but it didn't follow? Who remembers that? You want to say something about it? Don't use the chat, speak up. what other evidence you have that this benzene thing or cyclohexatriene thing is acting weird? Because, you know, we tried this, it didn't work. We tried that, it didn't work, which usually works on similar molecules. Like some chemistry that this guy will follow, some chemistry that this guy will follow. The same chemistry doesn't work on that. What chemistry are we talking about? Who remembers? Unmute yourself and speak up, please. I like interaction. I don't like to speak like a monologue all the time. What chemistry did we try on C6H6 that failed, but that works on double bonds, alkenes and alkynes? Who remembers? You can look up in your notes. Anybody? How many of you are there? 35. What chemistry did we do on a double bond, on alkene? We added some stuff, like two things came from sky and dropped on the double bond, and the double bond disappeared, became a single bond. What chemistry was that? Who remembers? It's an H word.
Was it hydrogenation or?
Hydrogenation. Does hydrogenation work on benzene? Doesn't work. Another reaction that's got a color, the reagent has a bright red color. When you add to a double bond and that species attaches itself from two opposite ends like this or like this, and the red color disappears, and chemists actually use it to check for double bonds and triple bonds. Like you add it, if the color disappears, you have a double bond. If the color doesn't disappear, you don't have a double bond. That chemistry doesn't work on benzene either, with this species either. What compound are we talking about? Speak up. It's a B word. Come on.
Boron hydration? I forgot how.
You're making things more complicated than necessary.
Bromination?
Bromination,
There
right?
you go.
There you go, yeah. Thank you, Hector and Jason. Bromination doesn't work on this species. So I'm going to write it down. If you try bromination, epic failure, doesn't work. If you try hydrogenation with a catalyst such as palladium, epic failure, doesn't work, okay? Because the double bond, even though benzene has 3 double bonds in that cyclohexane type of an arrangement, even though you have that, those double bonds are more stable. For whatever reason, they don't like to react like a normal double bond reacts, okay? Because of this strange arrangement, because of the cyclic arrangement and alternating double bonds, and there are a few other rules that we're going to be talking about after we erase the board now and go to the next board when we start the next discussion. That's why we can infer that under normal circumstances, bromination works on a double bond or a triple bond. Hydrogenation works on a double bond or triple bond. But this guy, even though it has double bonds, it doesn't react the same way. That means this molecule has some kind of strange stability associated, contributed by its special structure. There must be something about this arrangement. Carbon, 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 double, single, double, single, double, single. There must be something special, something weird, something bizarre going on with this arrangement that makes the molecule more stable than you had expected. You expected your child to be pretty rambunctious and pretty naughty, but it turns out that he's not that bad. He's better than what you had expected. So this arrangement was expected to be that bad, but actually in reality, it's not so bad. It's more stable than you had expected. And that stability is called aromatic stability. And that is what prevents benzene from reacting with bromine, hydrogenation, things like that. Okay, I'm going to take a snap of the board. I'm going to let you guys stare at the board for maybe 15 seconds. Then we're going to discuss taking to the next level. And feel free to ask any questions. I need a new phone. My camera takes like 1 minute to load. So far, so good. Any questions? You can throw it on the. I prefer that you speak up. Some classes, some other instructors are forcing you guys, students on Zoom, to keep their videos on. I don't want to make you guys that uncomfortable unless you really want to show up on the screen. That's fine. You can turn on your video. I don't know if I have forcefully turned it off. But then I think hearing yourself out is actually a good idea. So we talked about benzene, we talked about its shape, we talked about the original story with C6H6, the failed chemistry that started to make people worry about the structure. Eventually, Kekulé cracked the code from his dream, I guess, the dream of snake, that it's a cyclic molecule. That was a big deal at the time. I mean, we can laugh about it that, oh yeah, benzene is cyclic, everybody knows that. But at that time, it was a big deal. And then we talked about the fact that it was expected to be so much more unstable, but in reality, it is not so much more unstable. It's less than that unstable. So I'm going to start talking about that, and then I'm going to start listing the rules of aromaticity. What are the rules? What do you check in your mind? If I were a robot, how would I spot an aromatic compound? What would I be looking for? Okay, we're going to talk about that. So if you have any questions, unmute and ask, please. Don't ask while you're muted, because sometimes on Zoom that happens. I'm like, nobody's paying attention to me because nobody is hearing you out. Make sure you unmute yourself. Okay, looks like you guys are doing fine. So I'm going to erase pretty much everything and then start talking about the rules of aromaticity. Okay, I'm going to erase pretty much everything. Okay, so allergies are coming back. So what we're going to be doing is we're going to be writing down the rules of aromaticity on the right side. Sounds like a video game. Rules of aromaticity. It's like an ancient like mystic town. Doesn't exist, like virtual town. Rules of aromaticity. Okay, we're going to start talking about writing down the bullet points. So let's look. So this guy is, this guy is aromatic. This guy is not. This is. Even this guy is not. Think about how would you name this species. It's got alternating double bonds, but it's not aromatic. Cross means not aromatic. 2 check marks means it's aromatic. Okay. Then I'm going to draw this. you know that that's not aromatic. This, not aromatic. Even that is not aromatic. Maybe we should draw this guy in a similar way. Same color coding. This is aromatic. All right. Now let's set up the rules. Rule number 1. In order for a molecule to be aromatic, what comes to your mind first? What rule the molecule must be following? Who wants to say that? Who wants to come up with the first rule? This?
6 carbons.
Sorry, Eric?
You have 6 carbons.
Not necessarily. This, I must be on handcuffs. What am I trying to hint? I'm trying to drop a hint. I must be.
You have to be in a ring.
It has to be a ring. It has to be cyclic. Very good. Who was that? Megan. Must be. I'm just skipping some words. You can put it in later on, but you also will have the access to the video. So the molecule must be cyclic. Acyclic molecules and being aromatic, we don't know any such compound yet. Who knows? Molecule must be cyclic. That's very important. Rule number 2, that's cyclic, this is cyclic. They're not aromatic. This guy is aromatic. Why? What's the rule number 2? Who wants to be on the screen? I'm trying to look at the screen. So what's the second rule? Sorry, I didn't mean to block the board. What's the rule number 2?
3 double bonds.
Double bonds, but can you say maybe a little more professionally, like this guy has a double bond, that's not aromatic. This guy has 2 double bonds, that's not aromatic. We use the phrase in the beginning, on the brief.
3 pi bonds? Pi bonds?
Not 3.
Have 3
Alternating.
Yes, alternating double bonds. Must have, this is a little sketchy. I'm going to put the must in parentheses. There will be exception to this rule later on. Must have alternating. This is very important, that word, alternating double bonds. Good. Cyclic, alternating double bonds. Rule number 3. Rule number 3, this is my invention, okay? You won't find it in the books. So if I look at this guy, if I look at, let's say, look at this molecule, again, I'm going to erase it. This is not aromatic. This is not aromatic because you can say the answer in 2 different ways. You can say, well, Dr. Maitra, it doesn't have alternating double bonds. That's a good answer. That's very legitimate. That's fine. You will get full points. But what I want you to pay attention to is the fact that when you look at the part of the molecule that is problematic, this part is good. This part is good. This corner is good, and so is this corner, because it's got the double bonds. Because it's got the pi bonds, The unstable pi bonds, remember the pi bonds are made by side-to-side overlap of p orbitals, unhybridized p orbitals. And those p orbitals are very unstable. Wind blows and they go with the wind, okay, gone with the wind. They like to flow around. They can delocalize. They can get pushed to the left or right or up and down. We'll discuss that in a few minutes. That phenomenon is called, who remembers or who has heard it? It's an R word, when electrons are kind of floating around, spinning around, moving around. What's that R word? Anybody?
Rotating?
Say that again?
Rotating?
Not rotating. It's an, when you pull a string of guitar or viola or violin, and let's say the string is straight, right? If you pull the string up and you let it go, the string is kind of vibrating. There is also another R word to describe that vibration. What is that word called? It's a long word. Resonance. So resonance means when you're pulling the cable or the wire of that instrument. When I say wire, our son gets extremely mad at me. He says it's not a wire. So when you pull the cord and you let it go and it's vibrating, it's resonating. Resonating means at some point the cord is up. At some point the cable is down in a straight line. At some point the cable is down here. So it kind of forms like this shape, right? So at any time, the string can be found here or here or here or here. As you go closer to the points where the string is attached to, that length gets shorter. That area where you can find that point on that cable will be diminished, okay? So that's called resonance, because resonance means the electron can be here, or can be here. Why are we being so sketchy and so iffy about the location and the existence of the electron? Because the electron is kind of spinning around, moving around. That's called resonance. We're going to discuss it in a more proper way down the road, okay? So you can say that these points are little iffy, little problematic, because you can say there is no double bond. You can look at it in a slightly different way. What's that slightly different way? Well, around this carbon, you have nothing but sigma bond. That's a sigma bond, that's a sigma bond, that's a sigma bond, sigma bond, sigma bond, sigma bond, sigma bond. So around those two carbons at the bottom of that cyclohexadiene arrangement, those carbons have nothing but sigma bonds. And again, maybe this is a little premature, but I'm going to just throw it out to you, and I think you can handle it. The problem is that it's a secret right now. I mean, I didn't reveal that secret to the Monday, Wednesday class yesterday. I'm going to talk about that tomorrow to them and day after tomorrow to you guys. But I can tell you that one of the specialty about this arrangement is that this labile, that these sketchy electrons, this guy, this guy, this guy, this guy, and those two, those 6 electrons can spin around the periphery of the molecule. The hexagonal periphery, if you think about them like 6 poles around a house, think about it, it's like your house, like a little cottage out in the woods, and you have 6 poles, and in order for you to protect your house from wild animals, you have 6, don't laugh, 6 trained monkeys sitting on the poles. And the monkeys are not sitting quietly on the pole because they are monkeys. They're not like us, well-behaved human beings. One monkey is jumping from this pole to the other pole and pushing the other monkey to jump from that location to the next location. So the monkeys are jumping around, and it's kind of like a current. You don't see the monkeys. You cannot tell monkey 1 is on pole 1 or monkey 1 is on pole 2. Monkey 1 could be on pole 1 or could be on pole 6. The probability of finding monkey 1 on pole 1 is 1/6. So they're always spinning around, and when they're all spinning around, when the wild animals are coming and trying to ravage the house and find some food or whatever, destroy the house, they see this cloud and then they go away. So when you have the right number of monkeys spinning around the house and your electrons are flowing around the periphery of this cyclic molecule, they are stable. They are secured and stable. So I use this monkey example for the pi electrons. So the problem is there is nothing. When you have nothing but sigma bonds, you cannot have that electron flow through the sigma bonds. Sigma bond situation is like a sigma wall. I call it a sigma wall. Sigma wall is something that the monkeys cannot jump. Okay, monkeys can jump from one pole to another. Sigma wall is like a concrete wall or like a plywood or like a wooden fence that the monkeys cannot jump through. Okay, so they can't spin around. If they can't spin around, resonance doesn't happen. If resonance doesn't happen, the molecule is not unstable, then it's unprotected and unstable. Okay, so sigma wall, I'm just going to make it a new bullet point. So sigma wall is bad. Okay, I know that it's not writing very well. Sigma wall, whenever you see sigma wall, you can either say, well, it doesn't have an alternating double bond. You can either explain it that way, but in my exam, in our class in this semester, if you say, oh, Dr. Maitra, sigma wall problem, that's totally fine. If I ever write a textbook for organic chemistry, I'm going to introduce the word sigma wall. Okay, sigma wall is bad. So again, very quickly, cyclic, alternating double bonds, sigma wall is bad. They kind of connect each other. Somehow they're related. They're, one means the same thing, the other means the same thing, but looking at it in a slightly different way. Sigma wall is bad. Double bonds are usually necessary. However, these exceptions can work for an aromatic compound. Okay, what are those exceptions? Well, carbocation or carbanion. We're going to experiment, so no need to worry about it right now if you're not fully understanding what's going on. So instead of a sigma wall or a double bond, if you have a carbocation, a positive charged carbon or a negative charged carbon, so this means positive charged carbon, this means negatively charged carbon with a lone pair, it looks like a lone pair, or something with lone pair or lone pairs. So when you have a lone pair, that means you're not dealing with carbon. You are dealing with nitrogen, oxygen, sulfur, phosphorus, etc., that kind of stuff. So it doesn't only have to be made out of carbon and hydrogen. That's what I'm trying to say. An aromatic compound can have nitrogens. Aromatic compound can have sulfur. Aromatic compound can have oxygen. Aromatic compound can have phosphorus, silicon, all kinds of stuff. Not boron. It's not going to work. It may work. Okay, usually it doesn't work. So if you have a carbocation, if you have a carbanion, if you have a lone pair sitting on a nitrogen or two lone pairs on oxygen or two lone pairs on sulfur or two lone pairs on phosphorus, it might work. Okay, so watch out for those scenarios. We're going to discuss, and I'm going to make it really clear for you guys. Last rule, the last rule is super important. Last rule is the number of monkeys, number of labile electrons. Labile means mobile, L-A-B-I-L-E. Most books use the word pi electrons. I don't like to use pi electrons. I like to use the number of labile electrons. Labile electrons means number of If you're not familiar with the word, get familiar. It's like mobile. It's like not stationary. They're not stuck. They're not stagnant. They're moving around. Number of labile electrons. Okay, this last rule causes trouble, but I'm going to try to break it down and explain using a suggestion that one of your classmates from the past, I don't remember CHEM8 or 128B or 128B. I don't remember which class it was, but it was a suggestion from one of the students, and I liked it, so I adopted it in my teaching. So you check for all of that. You check for cyclic, non-cyclic. You check for alternating double bonds. You check for sigma wall. You check for carbocation, carbanion, lone pair, blah, blah, blah. After you have checked everything, before you label it, before you put the stamp, before you burn the stamp on your product, aromatic or not aromatic, you need to do one more test. One more. The last test is you count up all the funny electrons, all the monkeys in that periphery on the fence. How do you count the monkeys? You count all the pi bond electrons. You count the lone pair electrons. You count the negative charge electrons. For positive charge, there is nothing to count because there is nothing. You count 0, nothing. Okay. You count all the labile electrons, and the labile electrons are pi bonds, carbanion, and lone pair. These constitute the labile electrons. If you wonder like what electrons are we going to be counting, these are the electrons that you're going to be counting. Pi bond electrons. If you have a positive charge, you count 0. If you have a negative charge, you count 2. If you have lone pair, you count 2. If you have 2 lone pairs, you still count 2. We're going to discuss that in a second. I mean, imagine you have a fence with 6 poles, and one of the poles has like a Y, and there are 2 monkeys sitting there. And how many monkeys can participate in that monkey business? Only one of them. I know in the past, some of my students have said that this monkey metaphor doesn't work. So if it doesn't work, just don't think about it. Just think about the electrons. If it works, I'll be happier. But you don't have to please me. Do what you're comfortable with. So the number of labile electrons, pay attention. Let's say you count up the electrons. 2, 4, 6. In another system, it might be 24. Another system, it might be 18. Another system, it might count up to like 10. Okay? That number, you must be able to express that number, describe that number in this formula. What's the formula? This is where things get a little sketchy. It's not a lot of math, but then it gets confusing. That number, you have to be able to describe it as 4n plus 2. Okay. Relax, don't ask any questions yet. Let me explain. 4n plus 2, where n is 0, 1, 2, 3, 20, 4,000, any whole integer. Whole means not fraction. N can be any number that you can plug in. Okay? 4n plus 2. N can be anything. 5 million, sure. 10 billion, sure. 1 trillion, sure. 1, sure. 0, sure. Half, no. 3/4, no. So n has to be a full number, whole number, and you have to be able to plug it in. I'll explain. Once we go through some examples, I think things will get more clear how to use this last rule. So what it cannot be, n cannot be fraction. Okay? So these are the aromatic rules. Must be cyclic, alternating double bonds. Is it really etched in wall? Not really. It's not that hard and fast. You can have exceptions. Sigma wall, no way. Carbocation, maybe okay. Carbanion, maybe okay. Lone pair, maybe okay. Last checkpoint is you count up all the labile electrons and you try to express it as 4n plus 2. I'm going to explain that, okay? Let's look at the rules. And what I'm going to do is this is not that important, okay? So I'm going to erase the left side without taking a picture. You will get your time sword. So I'm just going to do that. So continue to look at the rules. All I'm going to do is erase the left side of the board and start applying the rules on a bunch of compounds. Okay, we're gonna draw up different compounds, and I'm gonna have you guys participate and see if we can apply the rules and figure out aromatic or not aromatic. Okay, number one, I'm gonna draw the molecules in one color. Is this guy aromatic? Yes or no? Speak up. Don't use the chat.
No.
No.
No. Okay.
No.
What's the problem? It meets rule number one. Rule number two problem, right? Okay. So let's say this is molecule number one. It's not. Let's draw another molecule. Let's use color. Just make things colorful. Molecule number two. Aromatic or not aromatic? Speak
No.
up.
No.
No.
Okay, why not?
There's not an alternative bond.
Be a little more professional with the choice of words. It's either it's missing something or it's got a problem. You can answer in different ways.
It needs a double bond.
It doesn't have what type of arrangement of double bonds?
It doesn't have alternating.
It doesn't have alternating double bonds, or it has sigma wall problem. You can answer. If I ask you that, if I throw like 6 compounds, let's say on Thursday on the quiz, you see a bunch of compounds, and I'm asking you to answer aromatic or not aromatic. Why not aromatic? Why aromatic? Well, this guy is not aromatic because you can either say it doesn't have alternating double bonds, or you can say it's got a problem. This part of the molecule is nothing but sigma bonds, 4 sigma bonds. So the monkeys cannot jump through the sigma bonds. That's the problem, okay? So either way is good. All right.
Yes. Yes.
Yes? Answer, one person at a time. Look at rule number 1. Does it satisfy rule number 1?
Yes.
Okay, so it's cyclic, good. Does it have alternating double bonds?
Yes.
Yes.
Yes. You're not done yet. We may stumble upon a situation where where the molecule is cyclic, it's got alternating double bonds, but it's not aromatic. So what do you have to check now? The last rule. Okay. Now we're going to practice that last rule. How many pi bonds does this species have? Speak up.
3.
3. 3 double bonds. So number of labile electrons is how much? What's the number of labile electrons? How many pi electrons are present? 6. Now the question is, can you write 6 as a formula for n plus 2? So I used to teach it in a certain way, And then my student in the past, I don't remember who that student was. She was a lady student and she suggested, Dr. Maitra, how about we solve the problem and find out the value of n? And if it is a whole number, it's aromatic. If it is not a whole number, it's not aromatic. I said, sounds like a great idea. So let's solve the problem. So can you write 6 equal to 4n plus 2? Okay, now write whatever the number of electrons you come up with, 6, 10, 12, 14, whatever, write it as equal to 4n plus 2 and then solve for the value of n. It's not that difficult. 4n on the right side, you know that when you move a number from right to left or left to right, it becomes negative. You know that. So you move 2 to the left side, it becomes 6 minus 2 becomes 4. So 4 equal to 4n, that means the value of n equal to 4 divided by 4 is equal to 1. That means, yes, you can write 6 as 4n plus 2, where n is equal to 1. That means when n's value is turning out to be a whole integer, not a fraction, that means what? What does it mean? That means it's aromatic. That's all it means. So you have checked all the important rules. You check that cyclic, you checked alternating double bonds. It already has alternating double bonds. Don't worry about sigma walls. Don't worry about carbocation, carbanion, lone pair, and all that stuff. It's waste of time because it already has rule number 2 satisfied. Then you still have to check the number of electrons because you might think it's aromatic, but it may not be aromatic. Is everyone clear so far?
Yes.
Okay. So this was the rule. How you calculate the rule. Let's look at the next molecule. Cyclobutadiene. This would have been cyclobutane. It's butane with 2 double bonds. I'm not going to ask you about nomenclature for that molecule. I just spoke it out because some of you might be wondering, like, how do you name that guy? Cyclobuta, B-U-T-A hyphen diene. Let's check the rules. Rule number 1, is it cyclic? It's cyclic. Rule number 2, what do you guys think? Speak up, say something.
Yes.
It is.
Yes.
It has alternating double bonds, right? Double, single, double, single, double, single. So it fits the bill. Is it aromatic? Should you jump to a conclusion that it's aromatic, or should you check something else?
Check number of labile electrons.
Number of labile electrons. What's that number?
4.
Let's see if you can write 4n plus 2. What's the value of n?
0.
So write down 4 equal to 4n plus 2. Then 4n
Should be 1/2, correct?
2. Then n becomes 2 by 4 equals half. Bad news. So that you can write 4 equal to 4n plus 2, provided n is half. Okay, it works when n is half. That's not how the rule is. That doesn't work. Half doesn't work. When n equal to half, that's forbidden. Okay, that's not allowed. That means not aromatic. Got it? Any questions?
Yes.
Okay, next molecule. You guys can still see this location. So I'm going to draw the next molecule. This should be molecule number 5. I'm going to spell it out here. Write down the whole thing. When you look at this molecule, do not waste your time going through the whole list. You should be able to spot the problem. This cyclopentadiene has a huge problem to be aromatic. What's that problem? Who wants to say?
Is it the sigma wall?
It's got the sigma wall problem. This is sigma, 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 sigma. That means this part is invincible. It cannot cross it. You cannot jump this fence. So it's got a sigma wall problem. Okay? So don't even worry about cyclic and alternating double bonds. It's not aromatic. As simple as that. I need little space. So it's got sigma wall problem. Got it? Priscilla? Okay. Last molecule. I'm going to just, for the heck of it, I'm going to change the color. You know what? Maybe I should not. This is molecule number 6, and it has a carbocation. Okay? What do you guys think? I told you that sigma wall is bad. You need an alternating double bond. You need a double bond. But if you don't have an alternating double bond, if you don't have a really sigma wall scenario, if you have a carbocation or carbanion, or if you have something with lone pair, it might still work. This guy has a positive charge. It might work. This is a recipe not for a disaster. This could work. But when you see something like this, you should check for the last rule. How many labile electrons does this guy have?
4, right?
Yes. 1, 2, 3, 4, nothing here. Carbocation means that electron is missing, nothing. So the number of electrons is, labile electrons is 4. We already saw that 4 doesn't work. It's not aromatic. One more. One more molecule. In this time it's not a carbocation, it's a carbanion. For some reason, this molecule lost a hydrogen, leaving the electrons on the carbon. Imagine a base coming, plucking the proton, whatever it could do. It plucked up the proton and left the electrons on the carbon. Okay, let's say this is molecule number 7. Can you work on that and give me an answer? We are almost getting to the end of our session. 9:12.
It would be aromatic because it'll be 6 labile electrons, right?
Hector, you're right on. So it's got cyclic. Rule number 1 is satisfied. Rule number 2, alternating double bonds. Well, we have 2 alternating double bonds. There's a little problem here. Well, it would have been a problem if it were all sigma wall. It's not a sigma wall because it's got a negative charge. That monkey can spin around. It's a strange looking monkey, but it's kind of a loner, but it can participate. Now, the next question is the number. 1, 2, 3, 4, 5, 6. we already found out that 6 can be written as 4n plus 2, where n, the value of n is 1. Therefore, this dude is aromatic. I wish I could stick one more compound and then call it a day. I'm going to try to stick the molecule down up here. Okay? I'm going to color code it as green. Let's say this is molecule number 8. This is the nitrogen. Okay? It's a legitimate compound. It's called pyrrole. It's present in bilirubin and biliverdin and many biological compounds. It's pretty cool. We can talk about that some other day. So this is called pyrrole. It's kind of like this molecule, cyclopentadiene, but instead of a carbon, you have a nitrogen here. And the nitrogen has how many electrons? Well, you need to connect all your dots. The early dots, intermediate dots, kindergarten dots, middle school dots, high school dots, okay? Number of electrons around nitrogen is 5, then it's neutral. 1, 2, 3, 4, and 5. The 4 and 5, the last 2 electrons stay as a lone pair, and these 3 electrons make 3 bonds. So one is making a bond with the carbon, the second one is making another bond with the carbon, third one is making a bond with the hydrogen, and the lone pair is sitting as a lone pair. What do you guys think about this molecule, pyrrole? Do you think this is aromatic or not aromatic? Check the rules. Rule number 1, cyclic. Yes. Rule number 2, must have alternating double bonds, no sigma wall. Well, it's got alternating double bonds. It doesn't really have a sigma wall. It has something weird with a lone pair, okay? So how do you count the electrons? 1, 2, 3, 4, 5, and 6. Aromatic or not aromatic? What do you guys think?
Aromatic.
Yes.
I'm going to take a picture. I'm not going to turn you guys off yet, and I can take a few questions if you guys want.
So you said every lone pair counts for 2, even if there's 2. If there's 2 lone pairs, it still counts for 2. You said.
We'll talk about that on Thursday. Yeah, if there are 2 lone pairs, if it were oxygen and it had 2 lone pairs, you count only one of them. We'll discuss that. I'm not expecting you to know that right now.
Okay.
No worries about that. Just know what we have covered so far. So the bottom line is the quiz on Thursday is going to pretty much cover aromatic stuff. 5 simple questions. Okay. Anything else? I'm going to upload the pictures. I'm going to upload the video whenever I have it ready, processed and on YouTube. And that's it. Any other questions? Speak up because I'm not looking at the screen yet. If there are no more questions, I'm going to hang up. Okay. Anything else?
Dr. Mitra.
Yeah.
I just wanted to make sure. I know you said we'll talk about it Thursday, but just for this right now, you said if it's a lone pair or a carboanion, it counts as 2, right?
Yes. If it is a lone pair or carbon-carbanion, then you count 2, because if you have a lone pair, because think about them like 2 monkeys. They can spin around. They can spin around with the rest of the double bond electrons. So this guy, this guy, this guy, this guy, and the lone pairs can participate in resonance or delocalization or spinning. We're gonna spend solid half an hour talking about resonance, at least half an hour one of these days. So yes, the answer is if you have a carbanion, you count 2 electrons. If you have a carbocation, you count nothing, count 0. So your counting will be 2 plus 2 plus 0, 4. If you have a carbanion, you count 2 plus 2 plus 2, 6. If you have a lone pair, you count 2 plus 2 plus 2, 6. Does it answer, Richard?
Yes, perfect. Thank you.
Okay, no problem. Anything else?
Not for me, Dr. Mitra. Have a good day.
All right, you too, and be safe and don't take any chances. Okay?
Will do. Will do. Thank you. You as well.
All right. Okay, take
Thank
care.
you.
Yeah, take care. Bye. I'm going
Bye.
to end the meeting right now. Shoot me emails if you have any questions. Do not hesitate. Regarding today's office hours, I'm not sure. I'm going to call my advanced medical imaging and then go from there. I'll send you guys an announcement anyway. I'll make up for the missing office hours at some other time, okay? All right. Bye. See you Thursday.